So in this session, I'm going to take the same gesture recognition dataset from the other day, but now we know that a dataset such as this can be seen as a set of logical interpretation of a given modal logic. That is, the only thing I have to do in order to make this possible is I have to operate some choices and choose the right transformer to see this as a set of Kripke instances, essentially. So once again, this is time series classification. So I have 360 instances, and each instance is a time series of 24 variables and 51 points. And if I make the assumption that I want to have a world for each interval that there is in this series, then I get this number of intervals, this 1300 intervals, more or less, and then yeah, I'm gonna play a bit with the minimum and maximum function, okay, because arguably they are the most interpretable functions, and they also have interesting properties. Okay, the current implementation of a model decision tree available in Julia is this non-alternating restricted model decision tree, which is once again able to learn these kind of formulas, and this is quite natural because that is basically saying there exists an interval with a property and another related interval. In this case, the second one, the second decision is not a diamond one. So actually I'm saying there exists an interval where P and Q, and from that one there exists another one with R, okay? But when we talk about intervals, we take the extensions of, we consider interval logic with the 13 Allen interval relations that you saw yesterday. And yeah, that's also part of the transformer in a way, and of the learning algorithm. So with this, so okay, again, if I load the data set, you know, I have 60 instances per class. The data set has 24 variables, 24, which I can think of as a table where I have 24 columns, and in each cell I have a vector. Okay, the instances look like this. So as I mentioned the other day, Kripke structures at the abstract level, not interval temporal logic, but the archetypical modal logic, where you only have one relation. You can model Kripke structures. You can see Kripke structures as having the frame part, which gives the graph-like structure. It's simply a directed graph. And the valuation, which assigns propositional interpretations to each world. So essentially, which assigns to each world the truthness of the atoms. So so first thing that I can do is I can query this data frame, and I can ask for an object which is the frame for the first instance, for example. Okay, I can also ask the one for the second instance, but in this case, all instances have the same number of points. That may not be the case in general. Okay, but then I get an object, okay, which I call a full dimensional frame. Why full dimensional frame? Because it's a very specific kind of frame. It has some properties that, in general, any graph may not have, right? Where actually that is actually defined by just one number, that is this the number of points. Okay, so what does full dimensional frame mean? So it's a frame, meaning that it's a graph. For example, I can enumerate all of the worlds in the graph. In Julia, I get a generator, so something that I can iterate, but I can also you know, unwind this generator and list the intervals. So of course, yeah, these are all intervals that are in the frame. But yeah, specifically, this object here can also model any dimensional domain in any n-dimensional domain. Okay, so this is quite something quite cool, that we can have the same we can use the same object for representing time series and images, or in general vectors, matrices, and even higher dimensional structures. They are going to be defined by more numbers. For example, with an image, you need two numbers, but the framework will still work, and you can enumerate worlds on those frames. Of course, if you lift to higher dimensions, you're probably not going to want to use intervals. You may want to use rectangles, and we are going to see something like that by the end of today. And I call this full because I'm also making the choice that I'm enumerating all intervals that there are. But this is arbitrary. I could also filter out some that, in some cases, it may be unnecessary to look at very small ones, because maybe they don't, in them there is not enough information for making an accurate choice, let's say. So, yes, but this is what we work with today. But in general, what is cool about Sole is that I think is cool about Sole is that at some point I could implement a new frame that is going to work on perhaps a new kind of data, and the same algorithms that I apply here will work there. Okay. So with a frame, I can also, of course, do the most important thing, which is to enumerate the accessibles from an interval. What changes from the other day is that now we have relations, right? For example, I could enumerate the intervals that come later than the interval 110. Okay. So what are these relations? This is the later that comes from interval temporal logic, HS. Here I call it IA because actually the definition of this comes from algebra, so it's interval algebra from the 80s. And what are relations? Well, just as many things that just as many things that are in Sole, there are just symbols that are used for for changing the behavior, some algorithmic behavior of the learning algorithm, let's say. Okay, and in particular, later is one of the interval relations which are defined in Sole, and I'm going to use in a bit. There is one relation, actually two relations, which are pretty important in Sole, and they are the global relation. What is the global relation? It's a binary relation via which a world accesses every other world within the frame. Okay, it has some properties, but never mind. So the point is that when you use, for example, the global. So if you start at this interval and you use the global relation, you reach every other interval. Okay, this looks super. I mean, why do we need this? No, because we're going to use this global relation, which, by the way, you can define as the union of the others, but that's another story, in conjunction with the others, because that's going to be useful for learning purposes. So the global relation is important. Another one that is important is the identity relation. Identity relation, simply, you start at the world, and it just enumerates itself. Okay. Not very useful, but like algorithmically, it saves some let's say some can make the way of writing algorithms more elegant. If I were to write a new algorithm, I would definitely make use of this thing again. So, and if I take a relation, of course, in the logic, in the interval logic, or actually in any logic, in any multi-relation logic, I cannot afford to use I cannot use. So this, if you remember, was something logical operator similar to I mean, syntactically similar to the propositional ones, right? Because it's just an object that has a symbol in it. And you know that when it when it appears in a formula, it's going to look like this. And that's all you know about it. But when you have a formula with many diamonds and many boxes, of course, you cannot, you're going to have many. And in particular, they are not just going to be symbols, but they are going to wrap relations in them. So for example, I can get, say, box L, which means, from my world, every world that comes later than mine had a specific property. So this is just a syntax token, and I can build formulas with this. I can give it an atom. Okay, and this. So I'm going towards the fact that we're going to learn formulas that have these objects in them. So a box, of course, I can have a diamond. I actually have, if I have a vector of relations, for example, interval algebra relation, notice that these are 12, not 13, but I can add the identity relation to make it complete. In what sense? In the sense that between any two intervals, there is exactly one of these that holds. Okay. Okay. If I have a relation set, I can diamond and boxes, diamonds. I can enumerate all of the 13 by 2 syntactical objects that I'm going to use in my formulas. Okay. Then, what's at the atoms? We have attributes, which when we learn are actually, we call them features, and they are scalar values that each world have. But if they come from a data set like this, where we have 24 variables and we make this choice, so these attributes actually are the combination of a feature function and a variable. Okay, so I'm going to call them features just because this is closer to the machine learning. I can't remember the word, but the dictionary. Okay, so yeah, for example, a feature that is the minimum of the first variable. Okay, I can have something that represents the feature of the first variable, and I can query my data and ask, for example, for the first instance, okay, compute this feature on an interval. Okay, this is easy. It's just going to do some slicing and then apply, in this case, the minimum function. Yeah, I could compute it on all the intervals. How do I do that? I just for I in all worlds, on all worlds in the frame of the first instance, right? All worlds. Okay. Oh, apparently also plot exports this name. So, okay, there are many, so it doesn't matter for now. But yeah, no, actually, yeah, it worked. It just didn't show me the answer. But when I learn formulas, I'm actually going to check many formulas on all of the instances. Well, not all of the instances, but I'm going to do many model checking. I'm going to call the checking function of formulas many times. So what I actually do is to make the transformation, because so far I was kind of interpreting computing feature values on this object, but I can actually transform it to a set of logical interpretations which we rebranded in logiset. Okay. So there is this scalar logical set function which can be which can make the transformation in many different ways. Let's see what this does. So we get a data set that, a data set of a few megabytes, which has an underlying frame of intervals, which has features at the worlds that are floating point numbers. Why? I mean, I didn't tell it what the features were, but they default to using the minimum and maximum. Okay, you can also compute different. You just feed the different functions, and it's going to compute them. But by default, you get something like this, right? You give it a few. You can give it a few functions, and they're going to be applied on every variable. You can also choose to apply some functions to some variables, because maybe you've done something priorly that tells you that some functions work better on statistically on some variables. But in this case, let's just stick with the default. It is prepared for like returning the answer to this question. So what is the feature value at that world for a specific kind of feature, in this case, univariate features, which are the ones that you saw. So simply take a variable and just apply a function to it. But even that is arbitrary. If you have an interval, you have many variables and many values for them. You could also use a neural network that looks at all of them, or just compute a combination of features that individually look at single variables. Okay, so we're still this is a very specific case, and it's good to know where we are in this space of possibilities. Full dimensional frame, number of instances. Okay, I'm gonna skip that for a minute, but no, not for 1 second, because actually this is a logiset that inside has two structures, and one is a logiset itself, and one is a memo set, whatever. So this is actually a structure that contains the feature values, and which act as my set of modal interpretations. So when I do the transformation, what happens is a bunch of features are computed on all worlds that are there. Okay, that are in the frame, and they are stored in this case in a multidimensional array, because I'm able to do that in the interval case. I may not be able to do that in general with any graph, but in the full dimensional case, I can do that with a compact structure. And that is good, because if I need to ask that question many times, then I'm gonna, it saves caching time to have the values all close together in memory. So this is actually what holds the information, but I can associate that with a structure that kind of remembers the results of checking. Why is this important? Say I have two formulas to check that are pretty similar. Maybe they have the same atom. Okay, we haven't discussed how the modal checking algorithm works in modal logic, but it makes use of memoization, which means that by the end, when you check the formula, you have some results, and maybe you don't want to throw them away because they can be useful if you check other formulas. So you just store them in memoization structures. Okay, and this is like the most generic. It's just a dictionary that can handle any kind of formulas. But then if we look at specific formulas like non-alternating formulas, there's an even better way of memoizing, of saving memoization values. And you can associate this logiset with actually stacks of different memoization structures that are used, that are basically cascading when you model check. Okay. So anyway, our atoms, in the end, what are they? They are conditions on the attributes, that is the variables. So scalar condition, you have a feature name, which may be the minimum of the first variable. And you can check, of course, on the logiset, an atom on the first instance at a given world. You can check if it's true or not, okay? Of course, you can compose formulas of this kind. This is a propositional formula. I can check it. Tells me whether it's true or not. Of course, I can use boxes and diamonds as long as they are relational, as long as they have the relations in them. I mean, it doesn't really make sense to use the anonymous diamond with no relation in it, but yeah, probably will never be useful. Yeah, so I can compose formulas, can check them. Right, so I can, okay, let's do this. Let's generate a random formula using the HS connectives, which are just diamonds and boxes of my 13 relations. Actually, my 12 relations. I don't need identity. And those in conjunction with propositional connectives, but weighted differently so that, because these are 12, they outnumber the propositional ones. So maybe I want to regulate how they are sampled. So I can generate a random formula. Okay, it will look like this. Okay, it happened to be a propositional formula, so something that I can check on an interval. Of course, I cannot check it if I don't specify a world, right? So when I learn from data, how does that work? I want to be able to learn any kind of formula, okay, that tells apart two classes. But I also have to learn in conjunction with that what is the reference world that I want to check it in. For example, I could say I want to learn a formula starting from the center of the temporal series, because maybe you can tell two classes apart because one has something in the second half which the other one doesn't. And okay, in this case, you can actually even learn that from the first world. But okay, let's say there is something that you can learn if there is a formula that if you check on the smallest centered interval, you're going to be able to tell these classes apart. But that's not the only way of doing it. For example, I could learn a global formula. So, for example, maybe I can tell two classes apart because there exists globally, anywhere, an interval with a given property where a formula holds. Okay, or maybe it's because every interval. Okay, there are a few choices here, but okay, for now let's just a random formula, and okay, I can check it. I can check it on. Let's take this interval because I know that every series in this case has 51 points, so they're all going to have this interval. Okay, in general, they may not be the case. Maybe some series will be shorter, so they won't. But in this case, they do. So I can check a formula, and if I don't specify the instance, which in a machine learning context, I don't want to look at specific instances, right? So I check it on all instances. It's going to be true and false on if I look at that specific interval, but that's so arbitrary. Why this one? Actually, what I want to learn is not the interval to check the formula on together with the formula, but together with the formula, I want to learn how to get what is the condition that I want to, how I want to check that formula. Meaning, for example, if it is the central interval, okay, then I learned the condition that you must check the formula at the center, regardless of how long an interval is. So it's not even the interval that I have to learn, but it's kind of the way of getting to the interval where you want to choose. Or you can do something else. Okay, so apparently this formula was true on 98 out of the 360 instances on that specific interval, okay? What if I ask, well, so I don't check that formula on the interval, but I ask, box G, meaning globally every interval has that property. Okay, if I do that, maybe that's too restrictive because it's not true on any. So some 98 instances have that at that specific interval, but none of the instances have that on all intervals. Okay. Plus, this is, yeah. Okay. What if I ask whether there exists an interval where that is true? Well, in that case, I can, something that I couldn't do before. Okay, yeah, here's what I'm missing. When I have a universal and an existential formula, I don't need the world to check it on. So it becomes really a property of the instance. Okay, it becomes a property, yeah, that can be either true or false on the whole instance. But in this case, the useful, like this formula here, the universal one is not useful because it doesn't. I mean, all instances do not satisfy that. I guess I forgot to say that I'm trying to come up with a formula that tells me something about these classes. Maybe I can tell them apart. If I go with the existential one, however, it checks through on 127, and yeah, so this says that there exists globally an interval where this thing is true. This is a propositional one, by the way. I mean, it's a global of something that is propositional. There's this function which is experimental and kind of translates this to natural language. So you could translate this to natural language. It says there exists an interval where blah. But for example, there are two implications here. Okay. So maybe difficult to read. Like here it says whenever that holds, also that holds, also that holds, or that holds. But luckily, there's this normalize function in Sole logics which tries to push negations downwards in the tree. I mean, actually, it can do many things. But if you give it the readability thing, it tries to make it easier to read. Yeah, and yeah, for example, you can use whether you like implications or ors, which are syntactically the translation is similar between one and the other. Okay, so if I normalize if I normalize this, I don't know what I get, but I didn't write it here. I think it was not interesting. But if I normalize the negation of it, okay, I get something that is actually readable and parsable from human mind, I would say. So on every interval, it is either true that this, or this, or this. I can parse that, right? By the way, yeah, we should be familiar with this. The only thing that I changed with respect to the slides is I'm using brackets instead of parentheses, and this is because when I parse these formulas from strings, I don't want those parentheses to bother me, because these are atoms, like atomic things that when I parse formulas, I don't want things that are syntactical in them, and the algorithm that we have for parsing would be confused by parentheses. Okay, anyway. Okay, so even if I translate it, stays on one line. And okay, so let's think about this. If I have an interval and I say the minimum of something is greater than, it actually means that all values for that variable are greater than, right? If I instead, if I have an interval and the minimum is below, actually the minimum is not greater than a certain threshold, it means that generally you may have values that are here, but that, like, if you take the values inside the domain, kind of reaches from above that threshold, right? So I can come up with shorter versions. So if I kind of say build intuitions, fast intuitions for these things, for these sort of these patterns, these things that may be, because here's the thing, there's a hidden quantifier here as well. So we have modal quantifiers, boxes and diamonds. We have Boolean, quantification that you can get if you combine. Maybe quantification is not the right word, but you have alternation at least when you use Boolean connectives to build concepts. But then even at the atom level, you have many values in the interval case I'm talking. But if you use a point-based logic, you don't have this problem. But for a single interval, you have many values, and so you aggregate. That's why you have many values. So you aggregate and compute a single one that is, in the case of minimum and maximum, it belongs to the domain. And if you use once again, and if you use an order, there's something, yeah. So if you build intuitions for what these pairs, the feature function and the test operator pairs, you can maybe get to something that you kind of read faster, reads faster. So this would be on that interval, actually on all intervals, V13, the 13th variable, reaches from above that at least that threshold. Okay.
No, I mean, I find reaches from above non-intuitive.
Okay.
Minimum value less than 10 just means that in that interval, you're going to have some value less than 10. The minimum value bigger than 10 means in that interval, every value is bigger than 10.
Sure, but if it's a temporal series, right? When I say reaches, it's because I'm thinking, okay, throughout, like through time, at some point, within the interval, it reaches the...
It might be always below 0.2.
Yeah, sure. I'm not saying it's strictly...
So I'm not sure reaches from above, but anyway, it's just...
okay. No, true. Okay, see, okay. I think I built this, so I think this is a good point, and this is because this formula was randomly generated, but okay, I have to think about it. I built these intuitions while working on the model decision tree, and I know that these things were chosen, perhaps you're right, yeah.
For me, the takeaway is, if you have feature atoms, like the minimum value of a variable is bigger than this or less than that, you should, and you want to understand the whole formula, you should at least understand what the atoms mean in your own way. I mean, if it said the average was at least a half, you should know what sort of average you're taking, okay? And maybe you want to break that down more, and maybe you don't, right? But you can't understand a formula if you don't understand what the atomic compositions are saying. So, I mean, I'm not sure there's much else to say than that.
Okay.
I mean,
so the point of transformers is you choose your own language that you should make sure that you understand. I mean, you do whatever you want, but the point of this is that for sure you must understand what the atoms mean and what, yeah, okay, and how to interpret the formulas. Okay. Right, so, and if I take that formula, so the negation of the existential of my randomly generated formula, it apparently appears to, like, I mean, I just look at this and it looks like it can tell the two classes apart from, it can separate two classes from the other four, okay? Yes, and this is the class distribution of the formulas that satisfy it. So, we have our first decision tree, which is better than chance. Okay, because I can take that formula, put it into, just simply make a branch, an if-then condition, which is what a decision tree is, a nesting of if-then conditions, where the conditions are formulas. And the so-called, so the so-called consequence, that is the things that it can output, yeah, in this case are strings. But in general, they also may be decision trees. But actually, any other symbolic model can be put there. Even a neural network can be put there. So actually, anything that you can put in the body of an if-then, right? So, but it must be a machine learning model in this context. So this has apparently an accuracy of 33%, which is better than chance. I just found it by randomly generating one. Yeah.
Why does it have? Is it if the formula is true, then return I have command?
Oh, okay. Because so I can see from the distribution of the labels of the instances that satisfy it that two classes would fall there and the other ones would fall there. And I know that if I pick one of the two for the as the label that I'm going to give to the instances that do not, okay, that's better than chance. So if I just picked one out of these two and one out of these four manually.
Manually.
No, yeah, I did it manually. It's just better than chance, right? I'm just playing with what the framework makes available.
Your definition of accuracy, proportion correctly classified or something?
Oh, yeah, exactly. So this is an if-then condition that that returns either that or that, given a single instance, and I just check whether that is the same as the ground truth. So my y's. Is it confusing?
So many instances have neither of these as labels. So that
No. Yeah, and they are going to be misclassified. That's why we have actually a low accuracy. Right? Yeah, it's not useful. I'm just playing with what there is. But
sure. I'm just
okay.
trying to interpret the numbers here.
Oh, okay. Is this clear? I just found a function that was in general true on instances belonging to 4 classes and was not on the other 2. So I take that and I build my own decision tree that just checks that, and then it says the best that it can do, that is one of the, in this case, one of the 2 or one of the 4. This is all very arbitrary, I agree.
Fine.
Yeah. When I have a decision tree, I can actually list the rules that represent its knowledge. So in this case, a decision tree, really, I would call it a branch because it's just, yeah. But a decision tree, in this case, it only has 2 rules. In general, yeah, you have a rule per path, and it works, as Guido mentions sometimes, by accumulating the formulas that you check and conjuncting them. So in this case, I get these 2 rules. And rules, by the way, are models, are symbolic models as well. So in Sole, I have many definitions of definitions for different symbolic models. There are rules, branches, and decision trees, which are just branches of a specific kind. I can have decision lists. We're not going to see these. Yeah, and you can play around with this. For the fact that you have this knowledge represented this way always allows you, for all these models that I've just mentioned, to obtain a list of rules with a specific property. And that property is that, so I'll say it again. If you take a symbolic model like the decision tree, you can transform it into a set of rules which have a property. And the property is that it's simple. These rules completely partition the instance space. If a new instance comes in and it can answer to the question of whether any formula is true or not, then exactly one of these is going to fire up. And if it fires up, then the instance is classified in a way, and I can look at the formula that is responsible for the classification. Okay, then I can, for example, I can build a second decision tree just by, I don't know, yeah, by nesting. Okay, meaning, yeah, what I mean is you can play around with, you could play around with discovering the knowledge yourself, but of course we're going towards the fact that there are algorithms for doing this statistically, right? I just randomly shoot out a formula, and it appeared to separate well these classes, but yeah. Another thing is to do it in a systematic way. So, but the idea of randomly generating a formula at any node can be used for designing a first decision tree learning algorithm. Right. So this is a recursive function which just generally randomly generates a decision tree with random formulas at the nodes. Of course, this is all unrelated to model decision the model decision trees that you have been presented. Okay, this is also agnostic of the logic almost. You could generate propositional formulas if you had a propositional logic set, a propositional data set. And also, this can be extended at the first order, as long as you can give me a representation of an object at the first order, slash the fact that maybe you must be able to check formulas. Yeah. Okay. So I'll speed it up a bit. So okay. Okay. In this case, I randomly generated. Yeah, but this actually worked better. So I generated a decision tree in a cart-like manner, but just I'm randomly generating formulas here, and I keep them if they separate something, okay? And then at the leaves, I just take the label that is more common. And apparently, I mean, it's a very stupid algorithm, but it managed to increase the accuracy with respect to what we had earlier. By the way, after all of this, some values were memoized in my structure. So I started with something that was 340 megabytes, and yeah, it almost doubled or something like that. Okay. Cart-like learning of model decision trees, and this is what this is the actual implementation of model decision trees that I was speaking about. But the current implementation, and especially with these Jupyter notebooks, I had to care about this. The current implementation, as much as it is optimized, tells us that we have to work with, for example, time series with a number of temporal points at most 50. So yeah, that actually okay, but it would be better if it was less. So in this case, I broadcast a function across my table that takes each series and it downsizes it to a 10-point series. And I do this by moving average just for to lower the, to hope that I can learn in less time. So then, of course, when I build the logic set, it's much smaller. And also, for the way that cart works, I have less values to iterate at each node when I want to learn the thresholds, the value that I want to learn. Yeah, remember that the cart algorithm would have to learn these thresholds from the data set. Whereas in these examples that I made, these come from the alphabet of these objects, of these scalar conditions that I fed my random formula generator. So what do I, okay, so how does it work in practice? Okay, here I'm just, let's take I have 72 instances that I use for training, just randomly sampled, and I test on the other 288. So 20% training, 80% testing. By the way, I mean, in many contexts, you would do the opposite. You would train on most of the data and test on the remaining smaller part. But so yeah, in Julia it works like this. You instantiate a model, which actually should be called the learning algorithm for the model. That's what I think. So yeah, if you import the package, you have this model decision tree, which is, yeah, it's both the name of the model and the current learning algorithm for it. And you tell it to use a specific kind of relation set. For example, you can tell it to use relations from interval algebra. You can also specifically tell it which relations you want to use, and the features which I think they default to this value. There are many other parameters to the algorithm. Some of them are really inherited from the CART algorithm and have to do with how much you want to overfit to your data. Others relate to what's the transformer that you want to use. Okay, so the concept of a transformer is currently hidden in these parameters. One day we probably have a more general infrastructure. Okay, so if I learn a tree with this setting, I get a tree that has an 80% accuracy in test. Okay, does it make sense so far? Are there questions? Sasha, any more questions? Okay, 80% accuracy. So, as Guido mentioned earlier, but let's remark it. So, if you constrain the model decision tree to have specific properties, you can actually visualize it in a more compact way, where each of those, wherever that appears in the tree, you simply like squash it. You squash the two layers together, and they look like that. So ultimately, we want to learn objects like that, which we call the implicit form of the tree, and then transform them to their pure version. So this tree has really simple semantics that I won't go into the detail here now, but if you're interested, we can talk about this later. Very straightforward semantics that are used for then making the translation from that object to a pure tree. And the pure tree has the most, let's say, the most straightforward semantics. That is if-then, nesting of the if-then. So you just have formulas to check. But we learned that tree first, and then we make the translation. So the tree that I've just learned in the implicit form looks like this. Yeah, I mean, this is the string representation of it. For example, okay, and by default, I can select the initial condition for the learning, the one that I said earlier. You could start at the center of the series, right? Or you could ask, there exists something. By default, we ask questions of whether there exists an interval with a property. Okay, I should speed it up, right, Guido? I don't know. Okay. So at every at every split node, at every internal node, what I have is a simple condition, which is of the kind diamond P, okay? And they nest in a straightforward way. For example, so say we learned that tree, okay, let's say there was a diamond in there. There exists P, and then you ask something of the intervals that you see, and then you ask something of the intervals that they see. Okay, so they nest in this way. So yeah, this is a condensed representation. I think it can be useful in some ways, but the pure knowledge is in its translation to the pure tree, right? Because this is really what you do in practice. Say that you found on your instance there exists an interval such as that. Then you want to ask something of that interval, or better, you want to ask whether there exists an interval. I know that there exists an interval with P in this case, where minimum of the first value has a property. But I want to ask something from there. Well, in this case, it chose to use G. It could have used the relations from interval algebras because I told the algorithm to use them. But it chose to go somewhere else and ask something existential. But for example, in the third case, when it ensured that these two things were true, then it asked something using the begins relations, which means that from an interval, you have a prefix interval with a property, okay? So it asked something starting from intervals that have these properties, okay? And if these three conditions are true, then this is the class. 8 training instances got here. 100% of them were spread wings, so that's why the algorithm decided to label that leaf as spread wings. This tree has 8 leaves, okay? And some classes are exactly classified by one rules. Wait, I haven't talked about the rules yet. Okay, maybe we'll get there earlier. Okay, no, actually what I want to say is that there are cases where the algorithm chose to split and to derive two rules in an implicit form, but both rules would give the same output. So it's the same as saying if that, then X, then something, else the same something. So I could just get rid of that branch and replace it with a leaf that says the same, right? Except maybe this is information that I want to know because it's actually clustering those further, and maybe there's a reason for that. I mean, in general, this is telling me that the instances for which something is true that I checked above in the tree actually split into 2 clusters. So maybe I want to know about the existence of the clusters of the cluster, or maybe I don't. And if I don't, I ask the pruning function to simplify it, so that I just get a leaf there instead of something that maybe I didn't need. I didn't need. Okay, then as I said, this why does it say leaves? Oh, okay, this is wrong. The number of leaves at this point reached 7. Okay. So when I enumerate the rules, I get 7 rules, okay? And yeah, while enumerating the rules, I keep track of the number of instances that were used, for example, for making this choice. The rules that apply where this formula applied, that number was 8. 100% of these were of this class, and this is additional information that I can add to my trees and later use for evaluation. Here I've just taken one of the. I just took one of the rules, and I can show that I can visualize it like this. Here there is also something more. So in this case, this says there exists an interval where something, and for all intervals something. yeah, it is very likely that if you're asking questions and there are a hidden minimum and a hidden maximum in there, I can choose to see them. It is very likely that this can actually be shortened onto a property to check on the whole series, because I mean we were discussing this earlier, but like if for example if all intervals have that the minimum is less than a threshold, then it's very likely that you can that this is equivalent as saying something of the whole series. So and in this case this means that I could also learn this this class using a propositional logic. We can discuss this if you want, but I mean it's a simple exercise anyway. Yeah, but in some of these rules, actually, you made use of the fact that you're using a more expressive logic. So, still, this doesn't mean that propositional logic would be better. In fact, statistically, it's not. Yeah, we touched upon that on this specific data set. We touched upon that the other day. Okay, so yeah, I get these, right? And especially when I want to classify a single instance, one of these is, I mean, arguably enough in a specific setting to justify the answer. Yeah, okay, this doesn't matter. Okay, the number of instances that I shown earlier, that 8 instances applied, the formula for the first rule applied to 8 instances. That was true. I'm talking about training instances. So, I mean, I can overfit. That 100% is not the confidence of that rule. But I can ask for what's the test confidence. So remember, I've learned these on 20%. If I use the other 80%, I can evaluate these rules. And I find that, for example, I can capture this class with a precision, that's a machine learning term, of 91%. And yeah, in general, for classes, I can capture them with a, I mean, capture them, we should talk about it, but we have, let's say, we have a rule for them with a high confidence, like say more than 0.8. But 2 classes, I don't classify well. Well, at least, so these 2 classes, not clear and all clear, I have 3 rules for them collectively. Actually, maybe this is a good rule, actually. It has 100% confidence. So there's a part in the tree where the algorithm tried to come up with something and it failed, okay. Some instances in training reach that point. What if I take those and I use another algorithm for learning any symbolic model, not even a decision tree? I can learn a decision tree, a decision list, a partitioner, anything that is equivalent to a partitioning rule set, something, or actually even a neural network now that I think about it. I can take that and I can replace it in that part of the tree. Okay, these two rules came from a specific branch, like the rightmost branch in the tree. And I would, and there's probably an explanation that has to do with the how limited the expressiveness of this restricted version of model decision trees is in there. Also, these 2 classes are very similar. It's the second and the third one. It's the same gesture, just one is pointing upward and the other one downwards. So there's an exercise in tree transplanting. For example, I could also learn that tree, if I'm lucky, with my stupid random decision tree routine that I've shown earlier. Yeah, that's it for this session. Questions?
I'm wondering, if you look at a rule that gets learned, right? So you said in the first stage, look, this if you've got these 6 or 7 classes, the classifier is not going to tell you what spread wings looks like. It's going to tell you how to distinguish spread wings from the others. But the pictures you had, the visual pictures you had right at the beginning when you introduced the data set actually showed what spread wings looks like. It was a picture with some arrows, right, which could presumably be described, I mean, in some, and I'm just wondering if one were to try and actually get rules which actually described the movement as it was defined, if that was your goal, could you use these sorts of, and first, do the rules even go anywhere close to these sorts of descriptions?
So I would say that if you look at the rule, you can at least, you know, relate it to the image that you have of that movement. There's a thing in machine learning called one-class classification, and we haven't been going in that direction, but I think that would be relevant in that case.
In general, the question is about generative, because if you have that rule, you can generate an image. Now, why this is not generative yet? Because as you say, the rule only distinguishes between the 6 classes that we have. Therefore, a random instance, let's say take a random instance at all, even if it satisfies one of the classes, won't look like won't look like any gesture at all, but it would have a very specific condition that it is the condition that distinguishes that class from the others. So yeah, we're a little far away from that yet, but that goes in the direction of generative machine learning, which is something that we were thinking about now. There is some work in symbolic, propositional symbolic learning that goes towards the generative, the generative direction, and we were starting looking into them to see whether or not it can be applied to this. But yeah.
Can I tweak my question?
Yeah.
Okay, so suppose I actually don't want to turn your rule into an instruction for how to do the gesture, but just into something visual, which will help, like those first pictures, which just tell me, look, if you see this, you see the left-hand tip always below there, and sometime later the right arm goes up, then you know it's this command and not those others. Is there a way to translate from your modal logic formulae, not to English, but to something visual?
Yeah.
Is that something that you think? You did it.
We did that in some other case, and the result is not always so appealing as it could be. But yeah, we tried that. Okay. With code, remember? We tried that with how the voice should look like if visualized in the case of infection versus the case not of non-infection. But because there are so many other details that the rules don't care about, and then you gotta give a value to them in order to I mean, probably something that you are thinking of, it wouldn't look like the person doing the gesture, but like if it was completely dark and then you see one light goes like this. So that would be something that makes sense. We didn't think about it this deeply enough to have an answer. What is this interesting? Yeah.
No, yeah. Also, let me mention that, like, in this specific data set, there is a spatial component that is completely hidden. So here you have, I mean, this is a temporal data set, but the person is moving in a spatial
in the space.
yeah. So.
Yeah.
So yeah, I mean, in your case, that would look. I mean, we don't know. I don't know if we can draw that in 3D. When I'm saying it, like, the question would be, can you draw the time series, right? Or like, can you trace?
The question would be if you can go back from time to space in this case. But
there's also the first step from that to.
That is, it just makes the question more difficult to answer, but it can be done. I think it can be done. What I think it's really interesting is it's that we've spent 1 hour talking about the model, which it would make no sense in non-interpretable models. That's the idea. We spent 1 hour talking about how the model looks like, what we can do with it, how can you trick it, how can you modify it, how can you interpret it. So this is what interpretation is about. The fact that the learned model is not the end of the exercise, but it's the start of the exercise. Whilst if you take a neural network, that's the accuracy. This number is the only thing you care about. You don't know how, why, and what can you do besides. I think this is the most important detail here, right? Okay, so what we have now, I think it's a good time for a break now. Yes, and after this, what we're gonna do is to throw in some other idea that makes all this something practical exercise. I'm gonna talk to you about. I'm gonna speak about feature selection in the dimensional case. So in general, in the model case, and then throw there some ideas about sampling and one more idea about multimodal learning. But it's going to take probably less than an hour, including the practical side. Okay, so let's break for 5 minutes, and we will be back.